thank you very much. I would like to begin by thanking the organizers for inviting us to this lovely workshop. Niccolò and I want to talk about algebra, and in particular, what is algebra? We agree that there is no fixed or universal definition, and our starting point is that its boundaries have shifted across history. But to answer this question, at least in a tiny bit, we think that there are sub-questions that are useful, such as what is algebra for? Does it have its own language, or is it a language? Does it have its own objects? And our talk seeks to contextualize algebra as a discipline, considering, let's say, both the perspectives of historical actors and those of present-day historians that interpret their text. And what we want to do is sort of foster a dialogue between two approaches to the history of mathematics, one grounded in the humanities and the other rooted in mathematical practice itself. And we believe that although these approaches differ, both are essential and that collaboration between them is crucial. Our idea for this talk is to focus on two historical case studies. The first will be Isaac Newton's conception of algebra, taking into account Newton's own context to better understand the task and values guiding his algebraic work. And the second is the Abel-Ruffini theorem, which established the impossibility of solving general polynomial equations of degree 5 or higher. And what we wish to do is to show how a shift in the task at hand helped redefine what algebra itself was about. So with that very brief introduction, I think Niccolò will start.
Thank you, Carmen, and thanks, of course, to the organizers for inviting us to this conference, to this workshop. So what I will do, without the help of slides, because it is beyond my competence to upload slides of that thing, I will wave hands and say something about Newton's conceptions of algebra, trying to play the part of the humanist, and we try to polarize this presentation in such a way that we probe different approaches to reading past text, and then in conclusion we will try to merge these two approaches. So my starting point is Henk Bos, because I greatly admire his work, and I will refer just at the beginning to a paper in a volume edited by Time, New Trends in the History and Philosophy of Mathematics, and Henk Bos has a paper there, Philosophical Challenges from History of Mathematics, which I think is an appropriate starting point. So the quotation that I lifted from this wonderful, short, and very informative paper is this. I quote, "Rather than, or perhaps in addition to," you see, it is not that Bos is proposing a royal road to the history of mathematics. He is saying, rather than, or perhaps in addition to reconstructing the mathematical concepts, we might attempt to understand the tasks which led mathematicians to form their ideas and to write the text we study. So there is a conceptual history of mathematics, what we might call an internalist, sorry if I use this term, history of mathematics, based on concepts, so the concept of function, for example, and we have beautiful histories of mathematics based on these ideas. But rather than doing that, we might try to understand the tasks which led mathematicians to form their ideas and to write the text we study. These tasks were self-imposed by the mathematicians in response to available knowledge, open questions, and more diffuse challenges. So what Boss was referring to was his work on the theory of the construction of equations that might be familiar to most of you. In studying Descartes, Henk Boss insisted on the fact that we misunderstand Descartes' geometry if we do not understand the tasks that Descartes had in mind. It is a book on analytic geometry, but we do not find the equation of a straight line only once, and we find many tracing instruments. In order to read this text historically, Henk Boss claimed, we have to understand that Descartes' tasks was construction. If we have a problem in geometry, we have to produce a construction by tracing curves and intersecting curves. So we have geometrical problems, we have a system of equations, we have an equation in the end, with this equation we'll have roots, but finding the roots is not the solution. We have to construct the roots. So Henk Boss studied the theory of the construction of equation, a theory that ended in the 18th century, not because its problems were solved, but because mathematicians self-imposed themselves different tasks. So these tasks were self-imposed by the mathematicians in response to available knowledge, open questions, and more diffuse challenges. They were therefore time-dependent. We have just seen that the theory of construction of equations disappeared in the 18th century. Indeed, it is difficult to imagine a Platonic eternal universe of mathematical tasks. Moreover, the tasks were governed by criteria of adequacy whose formulation was itself part of the general mathematical endeavor. So we have tasks and we have what was called the criteria of quality control. We have to self-impose ourselves, if we are mathematicians, criteria that tells us when, in which conditions we have achieved these tasks. So, after this praise for Henk Boss, I introduce our talk. And our talk, Carmen and I, we decided that our claim is that in order to understand the self-imposed time-dependent tasks and criteria of adequacy driving mathematicians, in my case, Newton's practice of algebra, we have to study the networks in which Newton operated, because it is in these networks that these tasks and these criteria were defined. We have to take into consideration, in my case, Newton's intended and real readers, to whom Newton addressed himself when he practiced algebra. And now, very briefly, I will wave hands and produce a toy model of an interpretation of Newton's algebra, because I don't have, I can pretend that this occurs because I don't have the time and not the scholarship to do that. But in any case, I will just, give you a very brief idea of what I might inflict upon you if I had more time to speak. So, Newton's algebra. Newton, as an algebraist, was active especially in the 1670s. More precisely, in December 1669, he had just been elected Lucasian Professor of Mathematics. He met in London John Collins, a mathematical intelligencer who kept very extensive correspondence with many mathematicians, and who was interested in algebra and in publishing algebra books. Collins, in other words, was a representative of what are called, using not a period term, mathematical practitioners. He was, an accountant who worked for the crown in several positions. His wife was a head laundress for the king, so she had a prominent position too, actually. So the couple was very well embedded into London life. And John Collins suggested to Newton to comment and improve a Dutch treatise on algebra translated into Latin. And Newton took this commitment very seriously and began corresponding with people who seldom appear in Newton's biographies, including my own. He began corresponding with people whose names are John Smith, not the best name for a historian when you search for him, but in any case, John Smith, who worked for the excise office, Michael Derry, a gauger, Anderson, and other people who had very practical concerns. Now, Newton's mathematical correspondence with Collins and with these people is known, but is somewhat backgrounded in the literature. So it's not a question of oblivion, but it's a question of backgrounding Newton as a person, as a mathematician who was interacting with mathematical practitioners, who had these concerns in mind. And he greatly respected them and produced also interesting mathematics by corresponding with them. For example, John Smith wanted to produce a table of square and cube roots, and Newton communicated to him interpolation methods that then became the Stirling-Newton interpolation methods. And it's a telling fact that we don't have Newton's manuscripts on these methods, but we have copies of his letters to Smith that were circulated and sent to Roger Coates, sent to John Kyle, and so on and so forth. So, in a way, an important part of Newton's mathematics disappears from his archive and resurfaces when you consider his network of correspondence. Now, in Newton, when Newton's early writings were published in the 18th century, many readers complained about the fact that these writings were written in a style that did not conform with what a mathematician should do, produce proof, demonstrations. You have a series of problems. I mean, Newton organizes his writings in the 1670s like that. Problem 1, problem 2, problem 3. And the problems are followed by rules and examples. It is hard to find demonstrations, so much so that people began to complain. For example, Bailly, in his Histoire de l'astronomie, writes, in one of his histoires, writes that Newton speaks in the manner of prophets. I mean, his mathematical style was understood as the style of the lofty genius who does not, explain things. Kramer, in his work on algebraic curves, says that it is disturbing that Newton did not explain his demonstrations, preferring to be admired rather than to instruct the reader. But Newton was writing in a style that was very much defined by his belonging to this, exchange of information with Collins, etc., etc. So, stop. Now I do another thing, that is, I consider a shift that occurred in Newton's life at the end of the 1670s, when Newton began reading geometry. He began reading Papus collectiones, he began praising the ancients, he began developing a strong interest in geometry. Now, these geometrical writings were shared with another network, a network based in Oxford, where there were editors of ancient mathematical Greek works, a somewhat different network that contributed to shape Newton's mathematics in a different way. In Oxford, John Fell, F-E-L-L, okay. He was the dean of Christ Church, eventually the bishop of Oxford, and I see that you are despaired because you are like that. But in any case, John Fell had in his hands the university press, and he commissioned to Edward Bernard an edition of Greek classics in 21 volumes. And Bernard conceived this big project, didn't bring it to completion. Bernard substituted Wren as a Savilian professor of astronomy in Oxford. And so a big project of edition began in Oxford. The result of this is that Wallis edited Ptolemy's Harmonics, for example. Halley edited the Conics of Apollonius. David Gregory produced an edition of Euclid. And Newton was, when you talk about Wallis, Halley, and David Gregory, it goes without saying that these are people who were very, very important in Newton's life. So the result of this interaction was Newton's commitment with the edition of the Greek classics. And Newton produced a solution of Papus' problem, a geometrical solution of Papus' problem. And he was so proud of it that he published it in the Principia. In section 5 of the Principia, you find Newton's solution of Papus' problem, hardly a problem that has anything to do with gravitation theory. And Newton added, there is a note in which Newton adds before the publication of this thing, I obtained this solution not by an algebraic calculus, but via a geometrical construction as the ancients required. Now, as the algebraic writings of Newton have elicited critical comments, so Newton's geometrical solution of Papus' problem is often criticized. Why? Because while Descartes' solution is easily generalizable to any number of lines, Newton's solution works only for 3 or 4 lines. Okay, so we have again, in order to understand this fact that Newton's text appears strange, we have to capture the tasks that he had in mind that were defined and self-imposed by the network of the editors of the Greek classics, who valued greatly the idea of restoring, of divining what the ancients had done. Halley's edition ends with a divination of the 8th book of the Conics. So, I have to stop here and maybe stop with a quotation, because this quotation is taken from a memorandum by David Gregory. David Gregory visited Newton several times, the first time in May 1694. And when he went back to Oxford, David Gregory was based in Oxford at this moment, he took notes in Latin about what Newton had told him. And so we have, Newton's ipsissima verba, so to speak. And Newton told to Gregory, our specious algebra is fit enough to find out, but entirely unfit to consign to writings and commit to posterity. These two lines capture what I told you in these 20 minutes. And these two lines are, an invitation. Then they can be taken as an invitation to approach Newton's text on algebra of the 1670s and his work on geometry as driven by values that had a meaning within two networks. And it is 2:25, and I think it's my pleasure to leave the word to Carmen.
Thank you. I would. I don't know how this works. My mic is not on? Yeah, picture. Yeah, they want to learn that. Yes.
Yeah.
You can't hear me? Yeah. No?
Yeah.
Is that better?
Very long.
Should I? Okay.
Should I turn minusing all this?
Is that okay?
Shall we? I don't think I should turn my...
I guess he's green or yellow. Red.
What should I do? Where is the maybe?
Look, I see you.
Sorry.
Thoughts or you should move within and thin.
Yeah. Okay.
I thought what you should do is to try. They'll make their feet. So you try now. But it's red. It's here. It's on. It's on. Yeah. It works. Yes. But for I can't. Oh, this is not. Yeah, but it doesn't do.
You on the frame. I'm not going to.
Sorry.
Sorry, tough.
Yes, now it works.
Yeah. Thanks. So, after that small glitch, I want to begin this second part of the talk with a treatise written in 1748 by Maclaurin. So this is a tiny bit after Newton, and I think this serves as a bridge between the two parts of the talk. And in this treatise, Maclaurin says that algebra is a general method of computation by certain signs and symbols which have been contrived for this purpose and found convenient. And he calls it a universal algebra. And I find this, I'm not going to read all that, but I find this very interesting if it's contrasted with what he says about geometry, where he says that in geometry, lines are represented by a line, triangles by a triangle, and other figures by a figure of the same kind. But in algebra, quantities are represented by the same letters of the alphabet, and various signs have been imagined for representing their affections, relations, and dependencies. So this sort of sets the context for what is happening a few years after Newton. And a few years after this, in the Elements of Algebra, I've taken the English translation, Euler writes that the principal object of algebra, as well as all the other branches of mathematics, is to determine the value of quantities that will be foreign known. And he concludes this small paragraph by saying that algebra has been defined as the science which teaches us how to determine unknown quantities by means of those that are known. So this is sort of how algebra is seen in the 18th century, let's say 100 years after Newton. So I I think we can say that the central aim of algebra was to determine unknown quantities from known ones. And this was closely associated with the expectation, I think, that every equation, regardless of its degree, might eventually yield to a method observed solution. Now, this assumption is profound in itself, and Euler himself worked quite a bit to try to show this, but it also has quite a history. Although I should mention that in Cardano, in his Ars Magna, recounts how Luca Pacioli had stated that a more general rule, in particular for equations of the fourth degree, was impossible. And Cardano says that he himself was deceived by Pacioli's claim. So even though there's this expectation in the 18th century that all equations will yield to a solution, a few centuries back, Luca Pacioli claimed that this would be, in fact, impossible. And this is Pacioli's text. It's Summa de Aritmetica, 1494. And he claims it's impossible. So senso is the square. So senso de senso is the square of the square. So that's the power 4. Essenso, so that's the fourth power plus a square is equal to the unknown, to the thing. And Luca Pacioli claims that it would be impossible to find a general rule to solving equations of the sort. And the same with senso de senso, e cosa, which is, let's say, the fourth power plus the unknown equal to the square. So, again, Cardano says that he was deceived by this, and then Cardano goes on to show Tartaglia's solution. But I think it's important that there's this point in history where people claim that it would be impossible to solve the equations of the fourth degree. Now, going back to where we were, in the same year when Euler publishes his Elements of Algebra, Lagrange publishes his Réflexions sur la résolution algébrique des équations, and in that text, which is divided into two, Lagrange reflects on the failures that have happened to enable the generalization of solutions for the cubic and quartic equations to equations of a higher degree. And he has a very important insight, and that is that the algebraic methods had succeeded in lower degree equations for very specific structural reasons. And what he wants to do in this memoir is to reduce these methods to general principles and to see a priori why these methods are successful for equations of the third and fourth degree, but they fail for higher degrees. And what he does in doing so is he sort of recognizes that the success of classical algebraic solutions was contingent, not universal, and that extended these methods would demand not only new techniques, but I would suggest a reconfiguration or a reconceptualization of what it meant to have an algebraic resolution of the problem. In the continuation of this memoir, published in 1771, he says, this is Lagrange, that the true principles of the resolution of equation are reducible, as one sees, he says, to a type of cálculo de combinación. And that is what I want to take to the next slide. No? Because this shift that Lagrange was announcing was to become more pronounced. If, in fact, algebra was reducible to what Lagrange says, then the failure to extend such combinatorial reasoning to general quintics posed a problem. And the established tools that they had at hand, well, they proved insufficient. And this insufficiency, it wasn't just a technical limit, but it suggested that a transformation in the identity of algebra, that is, the solution of equations, was needed. So we were moving from seeking solutions to sort of studying the organization of the equations and the structure of the equations seen as a whole. Now, moving a bit forward, this is a quote taken from Gauss in 1799, where he says that, and that's the part that I've underlined, that he didn't think it would be too difficult to show the impossibility of fifth-degree equations, and that he would come back to this in another text. He doesn't do that, but again, we have this idea, that was in Luca Pacioli, that this would be impossible to do, to have a general solution. And this same year came the first attempt to prove this impossibility. Paolo Ruffini published his paper where there's this attempt of a proof. There's a few errors in the proof, but the idea is there, no? That it will be impossible to find a general solution for equations of degree 4, higher than degree 4. And what I want to focus on is on how Niels Abel works on this problem. He was aware of this, and building on this calculus, this combinatorial calculus that Lagrange alludes to, and the work done by Ruffini, he approached the problem with the goal of providing a rigorous and general proof that this was in fact impossible. And I think we can summarize his method by saying that he analyzed the structure of functions that were formed from the roots and examining the possible permutations and then arriving at the contradictions under the assumption that a general solution exists for the quintic. He does this first in a memoir he published himself in 1824. It's a very short memoir. And then he extends this memoir in 1826 and publishes it in Niccolò's journal. It is longer and more detailed, and here we can find a systematic treatment of algebraic functions and their resolvents. So these two memoirs are what I will focus on. I want to go through Abel's proof in a very general way, and he considers a general equation of the fifth degree. We can ignore the signs, they are there for technical reasons, but we can assume it's a general equation of the fifth degree. And he assumes that the equation is solvable algebraically. That is, that the roots, let's call them y, can be expressed as algebraic functions of the coefficients, a, b, c, d, and e. That's what he assumes. And just to be rigorous and careful about this, he defines algebraic functions systematically. He's very careful doing this, using rational functions and the extraction of roots, and he only considers, for obvious reasons, prime indices. Then he shows that any algebraic function can be written like this. He does this in 1824, and in 1826 he's very careful and goes into detail. In 1824 he just says that this is possible. He takes n to be a prime number, p is a lower order algebraic function, and then the qi's are algebraic functions of lower degree. So any algebraic function can be written in this form. And then substituting that into the general form for y into the quintic yields an equation of that form, where again the qi's are rational functions of the coefficients and other auxiliary quantities. And what is very interesting once he gets to this formulation is that he shows that in order for this equation to hold, that is, for this equation to be equal to 0, he shows that all the qi's must vanish at the same time. And once he has shown this, this takes him to m expressions, m distinct expressions, where m is this number here, for the roots. So remember, we're calling the roots y, so he has roots y chi, and they are all of this form. And just as Lagrange had done, and Euler before him, look, these alpha k's here are the nth roots of unity, and they play a very important part in Abel's proof. So we are now at the point where we have these m expressions for the roots where they are expressed in terms of the nth roots of unity. And here, Abel uses a key result proved and published by Cauchy in 1815, which says that the number of distinct values for a non-symmetric function of n quantities cannot be less than the largest prime in n, that is the largest prime that divides n, unless it is 2. And then this implies, given that we're dealing with an equation of degree 5, that m in the previous slide can either be 5 or it can be 2. And there are no other possibilities. So Abel then takes to see what happens in either case. If m equals 5, he says, then we arrive at a contradiction between the number of values on each side of the equation. On one hand, we have 5 possible values, and on the other, we have 120. So he says it cannot be 5. If m were equal to 2, he takes the reduction to square roots, and again, combining these results by Cauchy's theorem leads to a contradiction. So now Abel is ready to conclude that the algebraic form of y cannot exist, and hence the general quintic is not solvable by radicals. It is an amazing proof. It is very, very interesting to study, and it's also very interesting to see how he sort of takes what Lagrange had said and systematizes it, so it is truly a study of how these combinations are working and why the structure of the roots itself says that the quintic will not be solvable by radicals. This is what I was saying. His approach, Abel's approach, relied on analyzing the structure of algebraic functions, not just the fact of how to solve them or what the roots were going to look like, but the structure of the algebraic functions taken as a whole, and how they behave under the permutations of root, rather than on trying to construct explicit solutions, such as, for example, as Euler had done about 50 years before. I think these memoirs mark a decisive shift from the task that was set in the 18th century, let's say from a formula-seeking task, to a structural understanding of what was really going on with the class of algebraic equations. And I think that two things emerge when doing this, that the study of commutativity, as we know it today, sort of surfaces as something that is key, because the group of permutations will not be commutative, and there is a symmetry here that is essential to understanding, or a non-symmetry, that is essential to understanding the actual structure of the functions and why this leads to an impossibility theorem. And I just want to finish this part of our presentation. Is what I want to show is how a negative result, which one could think would lead us to sort of the end of the road, this can't be done, so finished. Let's move on to something else. But there's a way of looking at this where we can say that this impossibility sort of plays a constitutive role in the discipline's identity as we see it today. In this case, it sort of redefined what algebra was about. No, it's no longer about solving equations and finding explicit roots of the equations. It's about redefining its objects and the methods used. No? So solving equations sort of gave way to a broader, and I'm going to call it more abstract vision. And the fact that historical actors like Abel moved towards structural and general perspective shows that algebra's identity was not fixed. As I said in the very beginning of this talk, it was historically contingent. And this itself shows why it's important to take into account the task set by the mathematician. You know, it's in this sense that we can take this theorem, which some call the Abel theorem, but I think Abel-Ruffini theorem is more appropriate. It sort of poses a historiographical challenge, and it prompts us to rethink how the shifting boundaries of algebra are drawn by the people who practice algebra or maths itself, and to approach the history not as the unfolding of something that's predetermined, a predetermined subject, but as a sequence of situated moments that in fact invite reflection on what the subject is and could be.
So, our is now to conclude 5 minutes. So I have to be very concise. And as you can see, what happened with our collaboration is that, of course, we framed our talks following very different methodologies, very different intakes. The intake of a mathematician, the intake of a humanist, let's say so. But I think both idea of tasks and self-imposed tasks and emerged in Carmen's presentation too. Now I would like to say something about Carmen's presentation, Carmen's case. It's interesting because it shows us how effective, how successful can be. Allow me to use, for reasons of brevity, this term, an internalist approach. I mean, the fact that doing history of mathematics, focusing on problems and how these problems were solved, is something that is perfectly feasible. And the fact that it works is something that is informative. We have to take into consideration this. Now, in the final part, I would like really to be very, very short, but I would like to envisage a research project that might merge our two approaches. So can we contextualize into a network that defines the purpose of algebra? Can we embed, let's say, Carmen's narrative into a more contextualized approach? And we discussed it a little bit, and we decided to concentrate on Ruffini. And I will be very brief. I will be almost, it is a caricature of a historical account of what we might do. But Ruffini is mentioned in the last concluding chapter of Massimo Mazzotti's latest book, Reactionary Mathematics, A Genealogy of Purity, in which Mazzotti defines a culture based in Naples. It is a micro-history of Napolitan mathematics, where very conservative, pro-king and pope mathematicians opposed the French analysis and defended, what Mazzotti calls a culture of reactionary mathematics. For these mathematicians and for Ruffini too, because Ruffini, he wrote a book on the immateriality of the soul devoted to the Pope. He was the deeply Catholic person, And he wrote also a book against Laplace, essai philosophique sur la probabilité. In 1821, Ruffini published this book. So he defended an idea of mathematics very much as the Neapolitan mathematicians, very much as Gaetano Agnesi, another mathematician, Italian mathematician studied by Mazzotti in his book Maria Gaetano Agnesi, Mathematicians of God. For these reactionary Catholic mathematicians, mathematics was a contemplation of truth. Our soul was created in imitation of God, and mathematics must be pure, must be a contemplation of truth, but it is also a way in which we probe the limitations of our knowledge. The 18th century, Laplace is the typical case, had a faith in progress, as a faith in generality, and what atheist or deist mathematicians like Laplace did was not to be aware of the limitations of mathematics. They applied mathematics to everything. They had an unbounded faith about the power of mathematics. So, the hypothesis that we formulated is that we might frame a history of Paolo Ruffini as a representative of this reactionary movement and his idea of mathematics as a practice that is aimed at contemplating truth, but also making us aware of the limitations of our reason, is something that resonates with the culture of another mathematician légitimiste, Cauchy, right? To quote the subtitle of a little biography written by a friend of a friend. So I think that we framed this idea as a possible way to merge our two things, and we wanted to talk for 50 minutes, and since we began 2 minutes late, and it is 52, I think, we did our job. So, great. So,
very good with the timing, that's clear. So, questions? Yes. Sure.
I wanted to ask if there is some historical hints that the shift you described in the work of Abel was recognized as such a shift at the time. I totally agree that from today's perspective it was a huge shift, but is there some sign in the correspondence or that such a shift was recognized as such at the time or in the following years?
I think so. I think Lagrange points to a shift being needed because he's pretty much convinced that there will be no solution, even though he doesn't point at an impossibility. There will be no possible solution if they try to continue down the road they were going. So, and given Euler's recent work and Lagrange, there's this, the ideas are there, the concepts are there without being named, that what they have to look at is this idea of how to combine the roots of unity to look at possible ways of moving forward. And I think after Abel, Galois certainly, it's just 4 years later, the shift is there, and it's clear. And I think I'm not going to say he calls it a shift, but he's completely aware, I think, of the fact that the field has to be reshaped. So yes, I think it's something that happens, perhaps not intentionally, but clearly, or at least in part, explicitly. They're aware it's happening, I would say. I think.
No, in the same sense, you think that the spirit of Galois in resolvent is another very different point of view than this of Abel?
I think it's sort of the next step. Sort of in the way in this morning they were talking about sort of the extension of what is happening. So Abel is very Abel's task is very specific. The proof of this not being possible, but the study of what is there, I think Galois just takes it to the next level. Just a few years later. So yes, I think it's in that direction.
We come to a view of that in the point of view of Abel.
Sorry?
We're talking about
Mathematician.
permutation of the rules that we polynomial.
That's what Abel does. He's aware that the roots of unity behave in such a way that that's what has to be done. And then he uses Cauchy's result to help him use the fact that the group is not a B and will lead to the contradiction.
Thank you for your presentation. Me, I also have a question about the case of Abel. Perhaps I missed something in your slides, and I missed perhaps the title of Abel's memoirs. But the question I have is that you point out that the shift is on the fact that we have we want before an explicit solution of the equation, and when we arrive to Abel, we have more something theoretic point of view. But the shift I can saw is in the previous title, like the one of Lagrange, the one of Euler, and the one of Maclaurin, for example, they use the word algebra. They use the expression algebraic resolution, but I'm not sure it's what we find in Abel. So what I want to ask is, we have before Abel, we are sure that the people make algebraic resolution, but in Abel, are we sure that he used algebraic methods or only algebraic objects? Because he defined algebraic equation, he defined algebraic functions, but how he practiced this thing, which method he used, perhaps it's not necessarily algebra. It's perhaps analytical or analysis for solving an algebraic problem, but it's not necessarily algebra. So it's the question if you also see this shift.
Thanks. I think it's a very interesting question, but I would go as far as saying that even in Lagrange or Euler, where it's clear that they're using algebraic methods, it's perhaps not that clear. The difference between algebra and analysis is something quite hard to establish. If we look, for example, in the same period of time, how D'Alembert defines algebra and how he defines analysis, it's very hard to see there's a difference. But going back to your question in Abel, I think I would call his method algebraic, because what he's doing is he's using nothing but the idea of what algebraic functions are, and then just counting these ideas or these values that emerge on both sides and seeing that there's a contradiction. But it is very straightforward that there is nothing but the idea of let's study the structure of this. And I think that's what algebra is. That's part of the change, but it sort of happens, if you ask me, in a very natural way. And the idea is present in Euler. See, and in Lagrange, this idea that we have to focus on this calculus of combinations. And it's, because Lagrange is very clear that just trying to find the rule to solve the equation will not be had. But there's nothing else other than this idea of combinatorics. I think that the next step happens with Galois, who sort of takes another step back and then looks at it and says, okay, this is what we're going to do now. So that's what I would say.
Okay, I think we have time for one or maybe two questions.
I have two questions, one in the form of a joke. About Ruffini and your concluding remark. So that's my first question. Do you think that Ruffini thought that God could solve algebraically fifth degree equation? First question.
Yes.
But second question, I'm trying to rethink everything that I've thought about algebra, and I was struck by the definition that Euler gives, that in fact you could very well interpret in the following way, that algebra would encompass arithmetic. So I do not see equation in this understanding of algebra, and this brings me back to Newton. Somehow, what kind of definition of algebra do you think Newton had in his practice that you have described of problems, rules, and so on?
Yeah.
Yes.
So it's me who has to answer this question. So first, the joke is of course funny, but yeah. So, but I have a few quotations from the Riflessione. Yeah, I have a few quotations from the book by Ruffini on the immateriality of the soul. And he says, it is from the Riflessioni Critica on the theory on the essay on probability of Laplace, sorry. So this is Ruffini in his criticism of Laplace determinism. And he says, I have an intimate conscience, I have an intimate conviction that I am free when I commit an action that is sinful or or I decided to avoid to do a sin. Now you say certain mathematicians, certain philosophers do not accept this proof of human freedom because it is based on an intuition. But what is mathematics? Mathematics is based on axioms. And we are convinced of the truth of axioms because we have the intuition that the axioms are true. And since our soul is created as, in imitation of God, we are basing mathematics upon, the religious conviction that our conscience do not deceive us.
Mathematics is based on axioms.
Yeah, mathematical reasoning is based on axioms, and axioms, i raziocini matematici dipendono dagli assiomi. Ora, come mai si conosce la verità di questi assiomi? Now, how do we know the truth of these axioms? Non al certo per altro mezzo se non per quello di una semplice intuizione dell'anima. So it is the intuition of the soul that convinces us that axioms are true. I'm not trying to convince you. I am not a reactionary mathematician, but what I want to answer to Carmen by saying that for Ruffini, mathematical knowledge is ultimately based upon intuition, the same intuition that convinces us that our soul is free. So And of course, he continues by saying, God has a knowledge which is noetic. Human beings have a knowledge which is dianoetic. So God knows all the truths of mathematics, but we have to reason, but we can know mathematical truths with the same certainty. It is the same reasoning that Galileo does actually in the prima giornata of the Dialogo. It is the same reasoning. And I believe that as far as I can see, I have been a Ruffini scholar for a couple of weeks now. So, but what I want to claim is that it might be possible to see Ruffini's mathematical practice as endowed of meaning from his point of view because of his philosophy, because of his theology in a way. Because in a way, mathematics is an artifact, but we endow this artifact with meanings that depend upon rather large cultural things, to say a truism, actually.
We don't have much time, so it's a very interesting reflection.
Yeah.
And maybe I can give you a quick question.
I'll try and be as quick as I can. Again, it's really a supplement to Karin's question about how Newton views the relationship between arithmetic, universal, arithmetic universalis, and algebra. There seems to be an extraordinary irony contained in what you drew attention to, which is this rather dismissive and instrumentalistic view of algebra, which Newton presents, actually states.
Yeah.
And the fact that Newton himself, in 1670, in his lectures on universal arithmetic, actually says, I quote, by the notion of number, I shall intend not a plurality of units, which of course was the old Greek Aristotelian notion of arithmos, of plethos arismenon, a determinate plurality of units, but the ratio of one quantity to any other taken for unity.
Yeah.
And Jakob Klein's great book on Greek mathematical thought and the origin of modern algebra, early modern algebra, draws attention to this as in many ways the decisive point at which the notion of number has changed in a way which has the most profound consequences for the future of mathematics. But really in a direction which has been made possible precisely by the algebraic standpoint.
Yeah.
And yet Newton is formally dismissing algebra as something purely instrumentalist.
Your intervention, just a quick comment about your beautiful intervention. There is often a tension between what a mathematician says about his mathematics, why it is valuable, why it is important, and actually the practice that it is often at odds with these statements in such a way that, for example, Newton was for many years a mathematician who dismissed Cartesian methods and wanted to distance himself from Cartesian methods, but he was one of the great heirs of Descartes. And in a way, he was a mathematician who framed his mathematics as a recovery of the ancient methods of analysis, but at the same time, both as an algebraist and as a geometer, he was extremely innovative. And so it is, we have to be careful in distinguishing the self-portrayal of a mathematician from the content and the practice of the mathematician. And that is why Carmen's intake is so successful, I think, because in the end, people who frame a cultural discourse about mathematics miss what mathematicians like Carmen see. I mean, they miss something that is actually independent from this, meta-mathematical level. And, we have to be aware, as Ruffini said, we have to be aware of the limitations of mathematics. In practicing a cultural approach to mathematics, we have to be aware of the fact that we do not see things that belong to mathematics that make mathematics independent. I mean, from the cultural context in which it is.
Okay, we should also take into account limitations of time. So we finish here.
Yeah.